These are all the topics that we're going to cover for the final exam, right? So we will start off with the overview of the stuff we're going to look at, and then we'll look at the properties and enhancing process like heat treatments, like the process that we can use to improve properties of metals like steel, right? And then we'll look at different shaping processes like casting and forming and machining, powder metallurgy, 3D printing of metals, uh, and then we'll look at joining processes like welding and surface processes. And we will have a brief look at the um, failure analysis of engineering components and a little bit on corrosion as well. Okay, so for today's class, right, we'll look back at the overview of our class, right? So I generally have told you about this since the beginning, right? So the concept of this class is that you should understand the relationship between the processing of manufacturing process, the effects of these process, right, and processing parameters from the process such as heat treatments, the forming process, and the welding process. These affect the structures, the crystal structures, the microstructures of a material, and when the structure changes, it will change the properties like the strength, ductility, toughness, etc. Right? And when the properties of a material changes, you will have different performance or application you can use it for, right? You can use it in like automotive industry, petrochemical industry, aerospace industry as well, right? So this is the key concept of this class, that you should understand the relationship between all these key pillars of this class, right? The process, structure, property, and performance. So well, as an engineer, when you want to design something and you want to produce that component, mainly you concentrate on the application of the performance of that component, right? But to achieve that performance, you have to think about the process. You have to choose the correct process because that process will influence the structures and properties and ultimately the performance, right? So you have to not just think about just the design, but also the manufacturing as well. Um, for example, the turbine blade in the jet engine, right? So because it is exposed to high temperature for a long time, you might get creep, okay, like elongation at high temperature, and then that is a failure of that turbine blade. But if you want the performance to be better, in other words, you don't want creep to happen, you have to think about what sort of um, structures that we can achieve that. Right? So we have to understand how creep occurs and what sort of property can resist creep. And one of the properties that can resist creep is the high strength at high temperature. At, at the same time, if we have a lot of grain boundaries, you have a lot of creep. So we have to think of a way that we can manufacture a turbine blade without having any grain boundaries. In other words, you need to produce a single crystal turbine blade, right? So uh, that it's our manufacturing process. When you change the manufacturing process, you get a different structure. In this case, you get a single crystal turbine blade with better property, better creep performance, right? So that's like an example of how these connect and relate to each other. So okay, so For the final exam, these are the topic that we're going to cover. Right. So for the manufacturing process, the manufacturing processes can be divided into two main categories. You have the processing operations and assembly operations. Right. We are mainly going to look at the processing operation, like metal shaping, right? Metal shaping, like shaping process, like casting or solidification process, particulate processing, like powder metallurgy, like metal. You use metal powder to form into the shape that you want. Um, um, Also, 3D printing of metals. Deformation process is a process that you deform a piece of metal into the shape that you want, like forging or rolling, etc. Material removal, for example, the machining process when you use CNC machine or lathe or any other machine tools to remove excess material to produce the shape that you want. Right, all these are shaping processes, right? And we're going to look at this uh, for this part of the lecture. And also we will look at the property enhancing processes, mainly heat treatments, right? Today we're going to look at heat treatment first, uh, and then we will look at all the shaping processes, and then we will look at the surface processes, like surface cleaning, coating, deposition. Right? So the the purpose of surface process is to produce a better surface in terms of aesthetic. I mean to be like to be nice to look at, and also better surface gives you better performance. For example, if you might recall when you learned about the um, fatigue, the mechanical properties and fatigue of metals. One of the one of the things that we can do to increase fatigue life of a material is by making the surface smoother, right? The smoother the surface, the higher the fatigue performance of a material. Okay, so these surface processing operations uh, improve the surface in terms of making it nice to look at and also have better performance. And you can also look at different coating process. For example, okay, for example, let's take an example of a turbine blade again. So the the temperature in the combustion chamber is really high, right? Higher than even the material used to make the turbine blade. And how do we prevent that material from melting in that uh, that combustion chamber in the jet engine? We do that by coat it with thermal barrier coating on the surface of the turbine blade to make it be able to withstand high temperature better. Right, so that is also a surface process. Okay. Okay, so all these processing operation gives you different components, and in the end, you have to put those components together. Right? You can do that by either permanent joining processes like welding, bracing, or adhesive bonding. Right? So these are the processes that you join them together permanently, or you can do it using mechanical fastening like nuts and bolts and threaded fasteners, etc. In this class, we will look at just the welding. Because of time constraint, we cannot look at all the assembly operations. Right? We will look at welding mainly, and we'll touch briefly just a little bit on bracing and soldering to give you a contrast of what what are the similarities and differences between welding, bracing, and soldering. Right? But we're not going to go into detail on bracing and soldering. but mainly we look at welding. Okay, so for today's course, we're going to look at heat treatments. Okay, so heat treatments are a bunch of processes that we can use to produce better property of our uh, material, right? And if you can recall, most metals, well, metals are divided into two groups. You have ferrous metals and non-ferrous metals, right? Ferrous metals are the uh, alloys which have iron as the main constituent, and non-ferrous metals are other type of metals. Like the non-ferrous metal might have iron as a constituent, but the iron is not the main constituent of that ferrous metals, right? An example of non-ferrous metals are, for example, aluminum alloys, titanium alloys, brass, uh, bronze, nickel superalloy, etc. So for ferrous metals, we uh, we have steels and cast iron, and usually the heat treatment can be applied to both steels and cast iron, and also to non-ferrous metals as well. Okay, some of these processes are specific to steels. Some of these processes are specific to non-ferrous, and some of these processes are like generally applicable to all type of metals. We'll look at all these processes um, today and next week. So the lecture note that you've just downloaded is the lecture note that we're going to use this week and next week, and then after that we'll have another set of handout to give it to you as well. Okay, so let's have a look at the heat treatments of ferrous metals, and we will take steels as our example. Okay, so the reason why we are taking steel as our example is because steels are one of the widely used engineering materials in the world today, right? So you have thousands of types of steels, and steels have a varying range of properties that you can choose from, and varying range of costs or prices that you can choose from as well. So that's why steel are still the number one widely used material in the world today, right? Not to mention steels are relatively quite cheap compared to other metals. Um, in fact, it's quite strange that steels are cheap compared to something like aluminum, because if you look at the Earth's crust, you have more aluminum ore than steel, right? You have more aluminum in the Earth's crust than iron. Uh, but it is easier to extract iron from the raw material, right? From the iron ore, right? So when you take the iron ore from the Earth's crust and then you want to produce iron or steel, it is much easier and much cheaper to produce iron than taking aluminum ore and then extract it into pure aluminum. One of the reasons for that is thermodynamics. Um, because the oxide of aluminum is very, very stable, so it requires a lot of energy to transform from aluminum oxide back to pure aluminum, right? Whereas the oxide of iron is not as stable, so it is easier, or it is more thermodynamically favorable to transform it back from iron oxide to pure iron. And we do that by using just heating it up with some uh, coal, right? Okay, so the coal will reduce iron ore back to iron, and we can and coal is really cheap, right? So extracting iron is really cheap. On the other hand, because aluminum oxide is really stable, so we cannot use the same process. We have to use electricity to reduce the aluminum ore back to aluminum. So it is more expensive. That makes aluminum a little bit more expensive than steel, even though the raw material of aluminum is more abundant and cheaper. It is more difficult to extract. Therefore, it is still a little bit more expensive than steels, and that's why steel is still the most widely used material in the world, right? In terms of weight, if you're looking at volume, the most widely used engineering material in the world is concrete, okay, by volume, but by weight, it's still the steel. Okay, so when we have a piece of steel and we want to change the property of that piece of steel to make it better, we have many processes that we can choose from, right? Today we're going to cover the full annealing process, normalizing process, spheroidizing process, and stress relief. Um, okay. Okay. Full annealing process is a process that we use to change the microstructure of a piece of steel. Um, okay, how do I? Okay, let's have a look at how we perform the process first, and then we'll look at why it is useful and what we do it for, right? So um, this is the phase diagram of iron and carbon, right? So we just take out the like one on the left corner of the phase diagram that 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 you've seen before, right? So let's have a look at phase diagram. See? Okay, so this is the phase diagram of iron and carbon, right? So we'll just have a look at this corner of the phase diagram, because this corner of the phase diagram is the phase diagram that is concerning steel, right? So we'll just look at this corner here. Okay, so we have this corner of the phase diagram, and you see all these lines. Yeah? We have A1 line, A3 line, ACM, etc. Right? The A1 line is basically the eutectoid temperature. Okay, this is the eutectoid temperature. The A3 line is the Solvus line, right, between the alpha and cementite phase and the gamma phase, right? And ACM is the Solvus line between the gamma plus cementite and like pure austenite phase here. Right? So if you look at the phase diagram, okay, in this phase diagram it doesn't show the phases, but okay, let's have a look at the phase diagram briefly. Right, so this is the same phase diagram, right? So above this A3 line and ACM, you have just the austenite phase, right? So this line here is the A3, this line here is the ACM, and this line here is the A1 line, right? 727 degrees Celsius, that's the eutectoid temperature, right? That's the A1, that's A3, and that's ACM. Okay, so above the A3 and ACM, you have the austenite phase or the gamma phase. Below the A1 line, you have the alpha and Fe3C or ferrite and cementite. Right? Okay, that's a quick recap. So now let's have a look at this annealing process. So for hypo-eutectoid steel, that means a eutectoid for a steel with the amount of carbon less than about 0.8%, right? So hypo-eutectoid means you have less carbon than the eutectoid composition, which is about 0.8, 0.78, or roughly around there, right? So for low carbon steel and medium carbon steel, we'll look at this A3 line, right? For hypo-eutectoid steel. And for hyper-eutectoid steel, we look at this A1 line, okay? So basically, for the steel, okay, let's have a look at the hypo-eutectoid steel first. So for the amount of carbon of less than about 0.8%, you see that you have to heat it up until the temperature is about 30 degrees above this A3 line. Right, so in this range. Okay, and for hyper-eutectoid steel, you have to heat it up until it goes above this A1 line, right? So in this range of temperature here. And the reason why you have to heat it up above the A3 and A1 line is because we don't want any alpha phase, right? So if it is below the A1 line, you have what, alpha plus Fe3C, right? And if it is above the A1 but below the A3 line, you still have alpha plus gamma here, right? So basically, you want to get rid of all the alpha phase. Okay, so you heat it up above A3 and above A1 line, right? So okay, so you have to get rid of all the alpha phase, and when you get rid of the alpha phase, all the alpha phase will turn into gamma phase, right? When you heat above A3 line, all the alpha or ferrite will turn into austenite. Okay, and here as well, all the alpha will turn into austenite because in this area here you have what, gamma plus Fe3C or austenite and cementite, right? Right, so that is the first step, right? The first step is to heat it up to get rid of all the alpha, and then you have to slowly cool it down, right? Slowly cool it down in this case means you just leave it in the furnace and then you shut off the furnace and leave it to cool down slowly within the furnace. And when you do that, what happens is that the grain will start to grow really slowly. You get a slow transformation, so you get bigger grains. Right? And when you have bigger grains, what sort of property can you expect compared to small grains? Hmm? Okay, when you have bigger grains, you have less grain boundaries, right? When you have less grain boundaries, it's more ductile. It's less hard, less strong, right? So when you do that, you induce softness. Okay, and you improve when you induce softness, you will improve machinability, right? So when it's less hard, it's more ductile, it's really soft. Now it's easier to cut or to mill it into the shape that you want, right? So that is one of the main reasons that we do the annealing process, full annealing, to make it softer so that we can shape it into the shape that we want much easier. Okay, and also it improves the electrical and magnetic properties as well. Okay, so when you heat it up at high temperature and then you slow it down, you cool it down slowly, you allow time for the electron spin to rearrange themselves, right? So that you get better electrical properties. Right? In fact, if you see this A1 line, you see this A3 line. In fact, there's a A2 line somewhere here, 700 something degrees Celsius. Right? Um, okay, and well, mm, okay, it's not really relevant in this class, but it's just an extra bit of information. Okay, you've seen the alpha phase, right? You see, and you also know that there is a gamma phase. Some people might just wonder, then where is the beta phase? Why you skip beta, right? You have alpha and gamma, and then if you go up in temperature, you have the delta ion, right? Where's the beta phase? In fact, the beta phase is very similar to the alpha phase. It's got the same body center cubic structure as the alpha phase, but the only difference is that the beta phase is non-magnetic, whereas the alpha phase is magnetic. So you have this A2 line somewhere around here, right? About 780, if memory serves me right, about 780 degrees Celsius. I mean, above this line, it's still a BCC structure, but it turns into beta ion, which is non-magnetic. But below the 780 degrees Celsius, it turns to alpha ion, which is magnetic, right? So you can see that when you heat it up above the A3 lines, you also heat it up above the A2 line, so that you will sort of reset the magnetic field within that piece of uh, steel, right? So, and if you could let it cool down slowly, you will allow it time for the electron spin to rearrange themselves in the optimum setting. Okay. Okay. So the full annealing process is used mainly for low and medium carbon steel, right? So you make it softer so that when you want to machine it or when you want to do some plastic deformation in terms of shaping process, you can do it much easier, right? Shaping or forming process like cold forging or rolling, etc. You have to heat it up until the temperature is above this line. You want to get rid of the um, alpha phase. In other words, you want to like sort of reset the microstructure, right? You might have a lot of small alpha grains in the beginning, but if you heat it up above this line, all the alpha grains will sort of disappear, and then you allow it to cool down slowly. What you get is um, well, a coarser grains. Right? You have a coarser grain. Um, you have a coarser grain and softer microstructure. Right. So okay. Okay. This diagram is called a TTT diagram. We will look at this diagram in a bit more detail later on, but for now, I just want you to concentrate on these two lines, the red line and the blue line, right? You see that the blue line has a slower cooling rate, right? Okay, the y-axis is the temperature, and the x-axis is the time in log scale, right? And also you have the red and green line. These are the transformation line, right? So we have temperature, time, and transformation. So this diagram is therefore called a TTT diagram, time temperature transformation diagram. We will look at this diagram a bit more in later on, right? But you can see that the red line is the start of transformation from austenite to perlite, and the green line is the finished transformation. And if you look at the slow cooling, which is the blue line, you can see that it will take longer time before the transformation starts, and then it will take even longer time before the transformation finish, right? Because of this slow cooling process, okay? And because of that longer time that it takes to start transforming and finish transforming, you get this microstructure, and you get a coarse perlite microstructure, right? Coarse means rough or big, right? So this is a sort of microstructure that you would get. A coarse perlite means you get a bigger perlite grains, and that is like a softer microstructure that you might get. Okay. So if you cool it down quicker, like moderately cooling, you get a fine perlite microstructure, right? This is a fine perlite microstructure. If you cool it down quicker, you see that all the cementite are like bunched up together, right? So it looks harsher, it looks darker, it looks harder, right? So the fine perlite is harder than coarse perlite. Okay, so that's sort of like a trailer of normalizing process, right? Anyway, so we've looked at annealing process, right? We heat it up above A3 and ACM. Oh, I'm sorry, A3 and A1, depending on the amount of carbon, right? So basically, we want to get rid of all the alpha phase. Okay, we don't want any alpha phase. We don't mind the gamma phase, or we don't mind the cementite phase, but we want to get rid of all the alpha phase. And then we cool it down slowly in the furnace. We just leave it in the furnace, shut down the furnace, and let the furnace cools down really, really slowly. We get coarse perlite, which is soft, okay, and it improves machinability of our steel. Okay, next we'll look at the normalizing process. Okay, so for normalizing process, it's a little bit different from the annealing process. This process, we want to refine the grains, right? To make the grains like relatively equal in size, and make the grains sort of like the grain size sort of more uniform, and and at a desirable size distribution. So basically, you have some sort of hardness or strength in mind, and with that hardness and strength in mind, you know what sort of grain size you want. Okay, so we want to heat it up and then cool it down relatively quickly to get that grain size. Okay, to get the designed microstructure and designed hardness. And to achieve that, we have to sort of reset the whole microstructure. So to do that, we have to make the whole structure goes back to all austenite, right? So when we heat it up for normalizing process, we heat it up above A3 and ACM. So this range of temperature. So 50 degrees above A3 and 50 degrees above ACM. So if you look at this if you look at this phase diagram, you can see that this is the range of temperature you need for normalizing process. And you can also notice that this is the phase field of austenite. So basically, normalizing process is when we want to reset everything. We want to start from the beginning. So we make the microstructure change back to austenite, and then we control the cooling rate so that we get a finer grains uh, microstructure of pearlites that is tougher and harder than the coarse grain microstructure. Right? Okay, so the temperature above A3 for hypoeutectoid and the temperature above ACM for hypereutectoid. Okay, to change it into austenite. Okay, then this process, this heating until everything changes to austenite is called austenitizing. Right? So you want to make it into austenite, so you austenitize it. Well, you don't really need to like remember the name austenitizing, but basically it's just to change it into austenite. Okay, so after heating into this range of temperature, you let it cool down, right? But this time you let it cool down relatively quickly. So you take it from the furnace and you leave it to cool down in air, right? So the cooling rate is much faster than leaving it in the furnace and like cool down at the same time in the furnace. Okay, so when you do this, you improve machinability, but not as much as full annealing, right? So this improved machinability compared to the steel that have been deformed when you have like plastic deformation, etc. You have a lot of dislocation density already, right? And when you do this process, you remove all those dislocation and you normalize the microstructure, and the machinability will improve a little bit. Okay. And you do this to modify the uh, dendritic structure of casting. Right? So because during casting you get some sort of dendrite or dendritic structure. Um, okay. Okay. No. The dendrite or dendritic structure refer to the structure that looks like a tree, right? Um, I'll look up some picture for you later on, right? So it comes from the Greek root of dendros, which means tree. The dendrite structure means the structure that looks like a tree. So you sort of have a like let's have a look now. Okay, so this is the dendrite structure that I talked about. So this is the here is the wall of the casting mold, right? So the casting will start to grow from the wall of the casting mold, and it will grow in this like sort of tree structure. So it sort of looked like a cross section of a Christmas tree, right? The fir tree. Um, uh, uh, okay, so this is the actual microstructure of the dendrite. You can see that it starts from the wall and go up, and then you have different branches, just like a tree. Okay, so when you have this sort of microstructure, the property is not isomorphous, right? So the property is not going to be the same in all directions, right? So somewhere around here, you don't have any like material, you have void here, right? The property is sort of better in this direction than in this direction, right? And we don't want that, right? So that's why we have to do the different uh, heat treatment process, like normalizing. When we do the normalizing process, when we do the normalizing process, we get rid of all the dendrite. So we sort of break off the different branches and make them into like different grains. Okay, so we have a more normalized, more equal grain size instead of like one long grains with different branches. Okay, so it will refine the cast of dendritic structure. It will refine the grain and homogenize the microstructure. So it will make the grains smaller and make the uh, microstructure more similar throughout the whole microstructure, right? So instead of like one area you have dendrite, one area you have different sort of structure. Okay. In fact, if you look at the casting, um, okay, okay, we will look at that in the casting. Well, in the next week we'll look at the heat treatment, and then the week after that we'll look at casting, and I'll show you the microstructure of casting and what happens then, right? So basically, normalizing process is a process that you use to normalize the microstructure. Normalize in this case means to homogenize, to make it similar throughout, to make it the same throughout, make the microstructure uh, uniform and make the grain size a little bit smaller to make it a little bit like stronger. Okay, so you do that by heating it up until everything changes to austenite and then cool it down in air. When you cool it down in air, you cool it down relatively quickly compared to when you leave it in the furnace, right? So you cool it down relatively quickly. So you can see that after a few seconds, right? After a few seconds, it starts to transform from austenite to pearlite. Okay, so you see that after less than 10 seconds, everything changes into fine pearlite. Okay. Okay, so this is the eutectoid temperature, 727 degrees Celsius. you can see that as you leave it, you take it out from the furnace at temperature above the A3 or ACM, right? So for eutectoid steel, 0.8% at a temperature above 727, right? So about 757, 767, or 780, somewhere around here, right? Or there, right? So 760. When you take it out and you leave it in air, the temperature will start to drop. The temperature will start to drop, and the temperature will drop below the eutectoid temperature. But you see that when the temperature drop below eutectoid temperature, it doesn't transform from austenite to uh, perlite straight away, right? It takes some time. You need undercooling, right? The undercooling is sort of a driving force for phase transformation, like in thermodynamics. You can think of undercooling as something that is similar to superheating as well. You have the thermodynamic driving force of the excess energy. Okay, so you have this undercooling. The phenomenon of undercooling that you might have seen in real life is when you have what's it called, um, beer wood. When you put the bottle of beer in the freezer for a long time, right? The freezer is at minus 20 degrees Celsius, minus 10 degrees Celsius. You leave it for a few hours. The liquid inside the bottle is at minus 10 degrees Celsius, below freezing point, but it's still a liquid. But as soon as you open the bottle, right, the temperature, it will sort of like transform into the more stable phase at that temperature, which is the solid phase. Right? In this case as well, when you have undercooling, it will transform into the the new phase, the stable phase, which in this case is perlite. Okay, okay, so when you cool it down really quickly, relatively quickly, you cool it down in air, you get finer microstructure, right? You have fine perlite, which is tougher than coarse perlite. Okay, okay. Next process is called spheroidizing. Spheroidizing process is a process that that turns the microstructure into spheroid. Okay, so well, you know what a sphere is, right? A sphere is like a globular shape, round shape structure. A spheroid is a spherical shape. So spheroidizing is a process to make something into spheroid in shape, right? In this case, in our microstructure, we have ferrites and we have cementite, right? Initially, it might be in the form of alternating layers of ferrite and cementite, so you get perlite. But for medium and high carbon steel, when you have a lot of cementite, right, your microstructure is really hard, right? For medium and high carbon steel, right? So from 0.6% carbon up to about 1.2, 1.4 percent carbon. You have a lot of cementite in the form of the cementite plates in the perlite structure. And also you might have pro-eutectoid or primary cementite as well. And that makes your microstructure really, really hard. And that makes it really, really difficult for the machining process. Okay. So do we have to do if we want to machine a piece of high carbon steel? We can use uh, an expensive like cutting tools like diamond coated cutting bits or milling bits that coated with tungsten, carbon, composite, etc. That is really expensive. Or what we can do is we can change the microstructure to be a somewhat softer microstructure, right? And we can do that by change the microstructure from this microstructure here, when you have like hyper-eutectoid microstructure, when you have perlite with a lot of cementite and also primary or pro-eutectoid cementite. You can change it into this microstructure, which is spheroidite microstructure. Right? So to change from this to this, what happened in the microstructure? You can see that the white bits, the ferrite bit, the ferrite bits, right, remains the same. You have ferrite and the sort of grayish bits here in the spheroidite structure. These are all cementites. So basically, what you're doing is changing the cementite from the lamellar shape or sheets or plate shape cementite. You make it into spheroid. You make it into like spherical shape. Okay. You take all these black lines, black plates here, and you change all those black plates into this like spheroid globular structure. And you can clearly see that even though this has the same amount of carbon, right? But you can clearly see that this structure looks a bit whiter. That means it looks a bit, well, it looks like it has more ferrite. It has a bit more, it has more ferrite structure, even though you have the same amount of ferrite, right? Because of that, it feels a little bit softer, right? So when you do that, right, the the cementite plates will turn into like smaller plates and spheroid in the end, right? And to do that is by heating it up to this range of temperature here, right? To a temperature about plus and minus about 30 degrees Celsius from the A1 line for medium carbon and high carbon steel, right? This range of temperature here. Usually around like 700 degrees Celsius, not less than that, right? About 710, 700 degrees Celsius. You heat it up at this temperature and you leave it for 24 hours. Right? You supply energy in the form of heating, and then you supply the time for the cementite plate to break down into spheroid. Okay. Okay, so when you do that, the steel will have the maximum softness. Okay, so because medium carbon steel or high carbon steel have a lot of perlite, which and in that perlite you have a lot of cementite, right? Especially in high carbon steel, in like hyper-eutectoid steel, you have pro-eutectoid or primary cementite as well, right? And that makes it really difficult for machining process because it is really hard. It is difficult for machining. It is difficult for forming and shaping process. It is difficult to plastically deform it into the shape that we want. We want to make it softer. We do it by spheroidizing. Right? Spheroidized steels have a maximum softness and ductility, and are easily machined and deformed. Right? Because now all the um, cementite plates turn into cementite spheroid. Okay, you have the globular form of carbide. Right, so basically the carbide that we are talking about is Fe3C or cementite, right? And because of that, the change in microstructure, you have this softer, more easily machined microstructure. Okay, and you can do the spheroidizing process from any microstructure. It doesn't have to start from perlite. It can start from martensite. Martensite is a very hard phase. We will look at martensite in a bit later in the hardening process, right? Or we can start from the ferrite and perlite. So this is for the hypoeutectoid steel, right? When we have about say 0.6, 0.7% carbon, it's still a medium carbon steel, but it is a hypoeutectoid steel. So you have primary ferrite. As you can see the primary ferrite here, around here, right? All these white area is the primary ferrite, and this area here used to be perlite. This area used to be perlite, right? This used to be perlite grains, but when you do the spheroidizing process, the perlite grains transform into uh, ferrite and spheroidized cementite. Okay, so this is this is the 1040 steel. You heat it at 700 degrees for 21 hours. Right? So 1040 means it's a plain carbon steel with 0.4% carbon. Okay, so it's a medium, sort of lower end of a medium carbon steel. Okay, all right, so that's spheroidizing. Okay, so the main purpose of spheroidizing is to make it as soft as possible for the machining process or for the shaping process. Okay, and next process is stress relief. Stress relief is, well, just as the name suggests, it's a process to release stress inside the piece of steel, right? Where does the stress come from? The stress come from the plastic deformation process. Right? When you turn it into the shape that you want, you might have to bend a piece of steel into the shape that you want, and by doing that, you introduce dislocation, and by the movement of dislocation, you introduce internal residual stress within that piece of component. Okay. Um, Another source of stress is by non-uniform cooling. For example, if your component have like one area which is relatively quite thin, and the other side is like relatively quite thick, so when it cools down, it's not going to cool down evenly, right? So you start to get uh, thermal stress developing inside your piece of component, and then eventually it develop into internal stress, internal residual stress within that piece of component. Okay. Uh, Also, you get stress from phase transformation. Right? When you transform from one phase to another, like from austenite to martensite, etc. Okay, so all these factors gives you internal stress, and sometimes we don't want internal stress. Okay, some other time we want a little bit of internal stress. Usually, internal stress that we want compressive residual stress, right? Because the compressive residual stress, especially on the surface, will improve fatigue life. But most of the factors that I've talked about just now, like the plastic deformation non-uniform cooling, phase transformation. Usually, this introduces residual tensile stress, which we don't want. Why don't we want residual tensile stress in our component, in our machine? Because when you have tensile stress, you tend to open up cracks, right? So if you have internal cracks, when you have tensile stress, you will open up that crack. Okay, so we want to get rid of the stress in our component so that the internal crack that we might have from defect or whatever doesn't open up when we are using it. Right? So we want to get rid of all the stress within our component. One of the way to do that is by heating it up and then cool it down in there. Okay, so usually we heat it up to about 600, 650 degrees Celsius. Right? You notice that the range of temperature that we choose to do the stress relief is a temperature well below A1 line, right? Because we don't want the microstructure to change, right? We don't want to change any microstructure. We just want to give it just a little bit of energy and a little bit of time so that it relaxes, okay? We just want it to relax it a little bit, but we don't want it to go crazy and change the microstructure. Okay, if we give it too much energy, say we give it a temperature above A1 line, right? So that now it has more energy, and that is enough energy to transform into other microstructure, and we don't want that. We want the microstructure that we have because of the property requirement and performance requirement uh, indicate that we want this microstructure, but we just want to get rid of the residual stress, right? So we just heat it up just a little bit so that it is still in the same microstructure, but any stress that we have will sort of dissipate away with time, right? You heat it up, it starts to relax a little bit. So basically, if you have a lot of dislocation, you heat it up to 600, 650 degrees Celsius. Uh, the atom will have a bit more energy than at room temperature, right? The atom will try to move and rearrange themselves to get rid of the dislocation. So you start to get like more or less perfect lattice again. When you get a perfect lattice, um, you get less residual stress. Um, okay. So, okay. Okay. This is not in your slide, but I just want to add something here, right? So if you look at this picture here, you can see this this location line, right? So when you have an extra half plane there, you introduce residual stress, right? So you can see that you have this uh, compressive residual stress here and like tensile stress here. And if imagine you have a lot of this, right? You have a lot of residual stress within your lattice, right? And when you heat it up in the stress relief process, all the atoms here will try to arrange themselves into a more perfect lattice, like the rest of the area, right? So you will get rid of these like strain field around the dislocation. Okay. Okay, so stress relief heat treatment is used to reduce residual stress. Right?